Welcome to Lab 3, Black Hole in Orbits. This lab was split into two parts. The purpose of part 1 was to find the mass of a black hole by analyzing the orbit and motion of a star around it. The purpose of part 2 was to model the motion of a spaceship in a figure-8 orbit around a planet and its moon. At the conclusion of this lab, an average mass of the black hole, was found and an orbit of the spaceship was configured. Fundamental principles used in this lab were the momentum principle, Newton's second law, and the universal law of gravitation. Some of the equations that were used were the rate of change of momentum over time, um, the final velocity equation in the form of Newton's second law, the force of gravity, universal law of gravitation, the net force, which is equal to F net parallel plus F net perpendicular. Here are the initial conditions for part 1. The system was the star and the surroundings was a black hole. For part 2, the system was a spaceship and the surroundings were the moon and the planet. And you can see the rest of the initial conditions here on this slide. The code for calculating the mass of the black hole is here to the left and right. We use the velocity and mass to find the momentum of the star, and from there the F net, not the F net, but the net force of the star, and afterwards the change in momentum over the change in time parallel was found by taking the change in magnitude of the momentum over time times the direction of the momentum. And F net perpendicular was found by taking F net and subtracting F net parallel from that, since we know F net parallel plus F net perpendicular equals F net. The mass of the black hole was found by taking the magnitude of the force of gravity times the distance between it and the star squared, between the black hole and the star uh, squared, and divided by the gravitational constant times the mass of the star. Here's the model of the orbiting star and the black hole. So I obtained that the black hole mass was 1.963 times 10 to the 34th kilograms. And you can see the F net, the net force and the parallel component for the purple arrow. And you can see the net force for the perpendicular component with the blue arrow. And you can see the net force overall with the orange arrow, which is the sum of F net perpendicular and F net parallel. And we can see that the perpendicular uh, component and the parallel component are perpendicular to each other, which is how they're supposed to be. Here's the code for the figure-8 orbit of the spaceship. We had to calculate the distance between the ship and the moon and the planet, and vice versa. We had to calculate these distances to be able to use the universal law of gravitation to find the force on the moon and the ship, to therefore be able to calculate their motion, in which we use Newton's second law with the velocity update formula, and then the position update formula, and from there that just calculated our figure-8 orbit. Here's the figure-8 orbit. You can see that the purple here is the spaceship, or the magenta, and the blue is the orbit of the moon. And you can see it kind of does a figure-8 orbit. It's not perfect, but that's it right there. And the initial velocity was found by taking the square root of 2 times the gravitational constant times the mass divided by the radius of the moon. What does it mean and what if? So the rate of change of momentum and net force can essentially give you the same values, but however, they are not the same thing. The rate of change of momentum parallel is equal to the change in the magnitude of the momentum divided by the change in time times the direction of the momentum. And the rate of change of momentum perpendicular is equal to the change in the direction of the momentum over the change in time times the magnitude of the momentum. The net force parallel is just the parallel component of net force, and the net force perpendicular is just the perpendicular component of the net force. They are not the same thing, but they can give you the same answer. What if, to calculate the motion of a multi-system of a black hole, star, planet, and moon, I believe it would be necessary to consider all forces that each exhibit on each other, And this will be similar to how calculations were done for part two of the lab. And in that sense, we had to think about the moon, planet, and the ship in order to make the figure eight orbit for everything. That's it for this lab, and thank you for watching.